In this video, we'll begin our discussion of section 2.6, part 1. There will be a part 2 right after this. These are about something called homogeneous polar differential equations. The reason that polar is there is, unfortunately, we are going to deal with another set of DEs later this semester that are also called homogeneous, but we don't call them polar. It's without. So we have to work our way up into what a homogeneous polar DE is. So the first thing we're going to do is talk about certain methods on trying to determine if a DE is homogeneous polar, and that will help us with the definition of homogeneous polar. So if I can write my differential equation like this, so the derivative on the left, that's fine. On the right just says some function where every input is y over x. It can also be x over y. Either way is fine. So it's, if you can write it in that form, then the DE itself is homogeneous polar. Now, that sounds like, okay, maybe that task isn't too bad, but actually it can be pretty difficult sometimes. So we actually have a different technique. This is the way I take every single time. Let's talk about just a homogeneous polar function of degree n. So if I can plug in, here's this function, let's look at this definition. It is homogeneous function of degree n if, notice when we plug in tx, right, and we plug in ty, we can work this out and work it around where I get my original function times t to the n. Like I'll have t to the fifth or t to the third or t to the first or t to the zero out in front of that, and that will tell me it's a homogeneous function of degree, whatever the power is. Now, how we use this, let's do an example. Right, I had my page on the wrong page. That's why I sounded surprised by the example. Determine whether, okay, we have this function. We want to know if it's a homogeneous function. So I'm going to show you how this is determined. What does that definition mean? So I'm going to take the function instead of x and y, I'm going to put tx and ty. So that means I go through everything here. Everywhere there was an x, I'm going to put a tx. And then the same thing for y, but ty. Everywhere the variables are. Just be careful on this. I've seen people make mistakes here, and it's sad. Like myself. To the third power, great. Now I start working this out. Okay, so I got 4 t to the third x to the third minus 2t squared x. Oh, we have multiple t's here. So we have t squared and t, that's t to the third, times x squared y. Plus, okay, I have a t squared there and a t, so I got t to the third. You've probably seen the pattern now. Minus, and then I get t to the third, y to the third, and in a classroom, this is where I would ask, what's in every term? Well, we have t to the third. So we have 4x to the third minus 2x squared y plus xy squared minus y cubed. Notice what's in parentheses is the function itself. So this is t to the third times f, x, and y. So this tells me f, that's therefore, by the way, therefore f is a homogeneous function of degree 3. So this is just a definition. There's nothing to understand except for when it has this property, it is called homogeneous polar. There's nothing like these functions do this or anything like that. Nope, just as right now it's a homogeneous function. If I can plug in tx and ty and get t to some power times my function. One thing to notice, and it's at the bottom of this page, but I'll just show you. If we look at each term, so let me highlight each term separately. Notice that the combined power of each term is 3. That is a clear indicator. If I have a polynomial and all the degrees add up to 3, or the same number, it's going to be homogeneous polar. Now, unfortunately, and I know some of you guys are going to be like, oh, that's dumb. You can't just say that. Well, look here, I can tell right there it's homogeneous polar. You have to show it by definition, and that's because this is what defines a homogeneous function. So there's no other way. You can't like wave your hands and say, hey, there's a 3. Like, we just noticed the pattern. Now, does it mean you can skip here to here? Yes. Please do. I'm okay with that. All right, so let's go to another example. So this one, All right, determine if it's a homogeneous function. So I am considering plugging in tx and ty, and I just plug everything in. Tx to the fourth minus 2 tx squared times ty squared. Right, we plug all that in, or we work all that out. T to the fourth x to the fourth minus 2 t to the fourth x squared y squared. Notice t to the fourth is in both. So we get x to the fourth minus 2x squared y squared, and t to the fourth, that is my original function. Therefore, f is a homogeneous function. I don't know what I was writing there. Function of fourth degree, or degree 4, either way you want to write it. Not too bad. The reason we're doing this is because we're going to use a homogeneous function to define a homogeneous DE, so we don't have to try to put it in terms of y and x. So let's look at example 3 here. I have h, x, y is that function, so we're just, don't let the h trip you up. Just h, tx, ty. And we just plug it all in. Nothing new. Squared minus ty to the third. And then I worked this out. I got 3t squared x squared minus t to the third, y to the third. And notice the biggest one I can factor out is a t squared. And we would have 3x squared minus, we'd still have a t in here. We can't write this as t to some function times h of xy. So from this, we just know that it's not homogeneous. All right. I have one more that's a bit tricky. Just there's a logarithm rule I want to show you within this video. So let's do example 4, the last one. For this video anyway. Determine whether this r of xy, don't let the r trip you up, is that function. Show that it's homogeneous, so it's the same thing. Tx, ty, and then everywhere they're at, I'm going to plug them in. ln ty minus ln of tx. Okay, there's a logarithm rule. I don't know if you recall. Log of a minus log of b, as long as it's the same base, base 10 or ln is the same base, we get log of a divided by b. So we can actually rewrite this. Let me fix that equal sign. Negative 2tx times, this is going to be ln ty over tx, using that logarithm rule. This is negative 2tx times ln y over x. Well, now I can just go backwards now, and I'm going to write it out this way. T times negative 2x times ln of y minus ln of x. Notice that is t to the first power times r of xy. All right, that's a 1, by the way. Okay, so therefore, r is homogeneous of degree 1. Let's try to write my g first. Of degree 1. So that's how you show a function is homogeneous polar. We are going to use this definition to find another way to show that a DE, a differential equation, is homogeneous polar. After we just define these last two things, then we'll start on the method to solve a homogeneous polar DE. This method for homogeneous polar is substitution method. I would have to say is probably the most important method. It's not this exact method, but methods like it. Those of you that will be working with DEs, wherever you may end up in your field, some of you guys may never touch this again. That's okay. Substitution methods are the way to go. That's what I've been reading in the current, like with articles within my field saying what engineers are using past this point. I do want to take this time, when you guys go on to your engineering classes, if you go on and you find out, hey, this teacher said, hey, I was supposed to learn this from differential equations. The teacher said you were supposed to learn it and apply it here. Email me, let me know that we didn't ever go over it. And then I can either tell you if we did or not, but I won't do that. I'll just say thank you for the feedback regardless. because I need to know if there's something that you're going to need in your future classes and your professor up there tells you that your DE professor should have taught you this. Please email me. Please text me. Please tell me. I know that's down the road, but I need to know these things. I'm not an engineer. I'm a mathematician. So I need to know what is helpful for your fields. All right.